This video is having a look at function dilation and reflection. So really we're just looking at the notation and how we get to the notation when we're dilating and reflecting functions on a Cartesian plane. So our success criteria are that we just want to be able to dilate in the x and y. So dilating means making it wider or skinnier, and reflecting in the x and y axis, flipping it around the x or the y axis. Now, the main point to remember when dilating and reflecting, because the process is actually the same no matter which one you're doing, it's just going to come out to a different result. The main point to remember is that the operation, so when you're applying whatever factor it's being dilated by or applying the reflection, you're going to apply it to the opposite coordinate to where it's coming from. So if you're dilating from the x-axis, you're going to apply the factor to the y coordinate and to the y part of your equation. It'll make a little more sense when you see a couple of examples. So if we start with dilating from the x-axis, so let's say we want to dilate by a factor of 2 from the x-axis, we would say that the point xy is going to map to the point x to y. So we're dilating from the x-axis, but we would apply our factor of 2 to the y coordinate of our points that are mapping to each other. So if you think about the equation y equals x squared, which is going to look something like that, we want a dilation factor of 2 in our x-axis. What that's going to do is effectively mean that if we had the point 1, 2, that point is going to map to 1, 4, because the x is going to stay the same, the y is going to be multiplied by 2. So if we had x equals 1 here, then our curve, so that's x equals 1, y equals 2, our curve, when it's dilated, is going to be up here. Right? So you're mapping it up like that in your x-axis. So you're dilating from the x-axis. So we're looking at the point where the x stays the same and the y is changing. So if we've got x dash y dash be the image of the point with the coordinates xy, so our dilated point, on the point we're mapping to, then x dash is just going to equal x, our x's will stay the same, and y dash is going to equal 2y. So when we rearrange that to put it in terms of x and y, we get x equals x dash and y equals y dash over 2. So remembering that we started with y equals x squared, that's going to map to y dash over 2 equals root x dash, which we can rearrange because conventionally when you're writing something in terms of y equals something, your equation, you want it to stay as y equals. So you would really want to rearrange that into y dash equals 2 root x dash. But because in this case, we're looking for the equation of the dilated graph, so we're looking for the equation of the image, then we just write it without the dashes and it becomes y equals 2 root x. So effectively, as a little summary box here, when you have a dilation of factor b from the x-axis, this is our rule here. So that the point xy maps to x by, or x dash equals x, y dash equals by. So you would replace y with y over b in your equation, and then when rearranging, you get y equals b times f of x. You'd be able to graph from that. When we're working with the y-axis, so dilating from the y-axis, again, if we were to sketch out that y equals root x, you'd have that. So now your point, if we were at, say, what were we, 1, 2, your new point, you would be looking at the sketch that maps it across, right? So the point 1, 2 would actually map to the point 2, 2, because our rule is that xy is going to map to 2x, y, because we're dilating from the y-axis, so our factor applies to the x coordinate. So our rule is that xy maps to axy. So effectively, if you're dilating in both the x and y, then you would have xy mapping to ax by. Exact same process when you're rearranging. So you would replace the value of x in your equation with x over a. So your equation becomes y equals f of x over a. And so we know that when we have something else in that bracket of the function, we can just replace it in the equation. So if we had y equals f of x and f of x equals root x, then this would map to y equals f of root x over a. If we were dilating like we had here in the x and y axes, our final equation here would become y equals b times f of x over a. This example asks us to determine the rule of the image, so the equation of the graph, when the graph of y equals x squared is dilated by a factor of 3 from the y-axis and then from the x-axis. So this is what the two of them would look like. Here we're from the y-axis, so our y-axis point would stay the same. Here from the x-axis, our x-axis point would stay the same. So when we're going from the y-axis, then we know that our point xy is mapping to, we've got a factor of 3 here, it's going to map to 3x. Why? Because remember, we're applying that factor to the opposite coordinate. So we know then x dash equals 3x, y dash equals y. So x is going to equal x dash over 3, y still equals y dash. We can substitute those into our equation. So it becomes y dash is going to equal x dash over 3 squared, because remember we're saying that here we have f of x dash over 3 effectively. So we're subbing in that x dash over 3 into our equation. And then we would want to simplify that. So y dash would be x dash squared over 9. And because we're actually finding the rule of the image, we just take away the dashes. So our rule is going to become y equals x squared over 9. For part B, we're reflecting from the x-axis. So we know our point xy will map to x 3y. And if we think back to the rule that we had just before, we know that we should end up with y equals b times f of x. So what we're expecting to end up with here would be y equals 3x squared, right? Just using our rule. To work that out, we know that x dash is going to equal x, y dash equals 3y. So again, we rearrange x equals x dash, y is going to equal y dash over 3. We substitute those into y equals x squared. So you have y dash over 3 equals x dash squared, which is just x squared. Then we rearrange because we want it to be y equals. So we'd have y dash equals 3 x dash squared. And because we're finding the rule of the image, not the translation specifically, we would just say y equals 3x squared, which is exactly what we said we should end up with at the start. When we want to perform a reflection rather than a dilation, all it is that we're saying, again, our rule. So if we're reflecting in the x-axis, we're applying that reflection to the y coordinate. So the point xy is going to map to x negative y. So effectively, all you are doing is replacing y with negative y in your equation to say y equals negative f of x. So over here, our example, we had as an original equation, we had y equals negative root x. We've wanted to reflect that in the x-axis, so we've applied y equals negative of negative root x, which is just going to become y equals root x, which is what we have up here. We want to do that in the y-axis. We apply that negative to the x coordinate. So x dash is going to equal negative x. So here our original function was y equals root of negative x. I realize that is not possible right now, but go with it. So we've wanted to reflect that in the y-axis. We've replaced the x with a negative x, so we ended up with y equals root negative of negative x, which is just going to be root x. That's what reflects it there. So as a little summary for you there, for the graph of y equals f of x, you have a list of each one of your processes to dilate or reflect. So if you want to dilate in the x-axis, you get y equals b times f of x. Dilate in the y-axis, you get y equals f of x over a. Reflect in the x-axis, you get y equals negative f of x. So you're negating the entirety of f of x, whatever that may be. And reflecting in the y-axis, you're just negating the value of x that's in your equation. So whatever f of x is, we make the x negative.